Okay, next up we have the 5 electron pair. So let's look at the basic shape first. For 5 electron pair, right, it is actually a combination of 3 electron pair and 2 electron pair. So in total, we have this shape over here, right? 5 electron pair. Okay, so you can see the green balls are like trigonal planar, right? 3 bond pair. All right, and then the 2 gray balls are like linear, right? Linear. Okay, so you have trigonal planar plus linear. This shape is called trigonal bipyramidal. Trigonal bipyramidal. This particular shape has 2 bond angle, which are 90 degrees. Okay, from the axial atom to the planar atom, equatorial. So this shape is 90. All right, between the green balls, right, you can see here, it is about 120 degrees. Okay, between the green balls, 120 degrees. So 2 bond angles for this particular shape. Let's take a look at the shape. Trigonal pyramidal. So I made use of like dotted lines to show that it is a plane. Okay, it's an equatorial plane, but you can also make use of like wedges to show this particular shape. Okay, no harm done. All right, so let's look at the advanced shape. Okay, imagine, right? Imagine if you have to put a lone pair in, right? You need to decide whether to put it on the axial position or the planar position, either the gray ball or the green ball. Okay, the overarching principle here, right, in VSEPR is to make sure that you have minimum repulsion. Minimize the repulsion. What kind of repulsion? Those repulsion which the bond angle is very close together. For example, 90 degrees. So we want to minimize this 90 degrees repulsion. So if we change this gray ball, right, to a lone pair, you're going to have three lone pair bond pair repulsion at 90 degrees. Okay, which we don't want to have. Okay, that's why we're going to substitute the lone pair here on the green ball so that you only have 2 90 degrees lone pair to bond pair repulsion. All right, so this is how we will substitute. Can you see? All right, I run out of green balls, so we're gonna use yellow and red balls here. So from the lone pair, right, to the bond pair here on top and bottom, there's only 2 90 degrees lone pair bond pair repulsion. All right, so this shape is superior to the one where you have 3 90 degrees lone pair bond pair repulsion. Okay, so this is the shape that we will take, and it is actually called seesaw shape. Okay, because it does indeed look like a seesaw. So if you put it like on a plane, it does indeed look like a seesaw. Can you see? Like a seesaw. Okay, but some schools of obviously in chemistry we want to sound like a very professional, right? So we call it a distorted tetrahedral. That's also fine. So the bond angles are all slightly compressed because of this particular lone pair over here. Exert some repulsion, exert some repulsion. Okay, so the angles respectively will be lesser than 90 and lesser than 120. Okay, the next shape we'll look at is what happens if we have 2 lone pair. Okay, going by the same logic, right, we want to substitute another lone pair into the equatorial plane. So we come up with this shape. Notice the 2 lone pair is on the plane. And then now, what does this shape look like? Okay, if you just focus in on the bond pair, this shape is just a T shape. Okay, just a T shape. All right. So let's show this particular shape here. The bond angle, as usual, will be lesser than 90 degrees because of some slight repulsion from the 2 lone pair towards the bond pair. All right, this is T shape. Okay, last but not least, what happens if we have 3 lone pairs and 2 bond pairs? Okay, we're again going to substitute it on the equatorial plane. So we're just left with these 2 bond pair, which basically is just a linear shape. All right, just a linear shape. Okay, so the bond angle snaps back to about 180 because we are just considering the 2 lone pairs. Sorry, 2 bond pairs.